This is Mbowa Joseph presenting number 2, and in this clip I'm looking at part A, which is about vector spaces. What is a vector space? A vector space is a collection of objects called vectors on which we have two operations, vector addition and scalar multiplication, and the operation must satisfy the following properties. There are only two operations we are looking at, that is vector addition and scalar multiplication. Any vector addition will always be commutative. Any vector addition must always be commutative and associative, and there must be a zero vector. So a zero vector plus any other vector will always get that other vector in case we are talking about u. And if you have vector u and you had the inverse of vector u, you'll get a zero vector. Then those are the properties for addition. Then we must also look at another property, and that is scalar multiplication. So all scalar multiplication must be distributive and associative, and there must be an action of 1. So 1 times vector u, you will always get vector u. When we come to a subspace, what do we mean by a subspace? A subspace of a vector space W is a subset V of W which has 3 properties. And what are those properties? If it is to be a subspace, the first one, there must be a zero vector in V. The second one, V must be closed under vector addition, and then the third one, V must be closed under scalar multiplication. When we come to our question to determine whether in each of the following subset V is a subspace of a vector space W. So when you look at our question, V is a subset of geometrical points x1, x2, x3, 1 in homogeneous space W is equal to R4 with vector addition and scalar multiplication given by x1, x2, x3, 1 plus y1, y2, y3, 1 must be equal to x1 plus y1, x2 plus y2, x3 plus y3, then 1. And also for the scalar multiplication is shown below. So we are talking about homogeneous space. What do we mean by homogeneous space? Homogeneous space W is a space with a transitive group action by an algebraic group. So if you have a group action, maybe group G operation, maybe W is mapped to W is transitive if it possesses only a single group orbit. And there are very many examples for homogeneous space. You can talk about hyperspace, hypersphere space, complex projective space, a real Grammanian of k-dimension subspace, and right now we are looking at R4 is also homogeneous space. Remember, the most important vector spaces, they are always noted by R1, R2, R3, R4, R5 up to Rn, and if you are talking about R4, it contains all column vectors with 4 components, and this is called a 4-dimension space. and we are looking at this 4-dimension space. In our question, we need to show that this vector V is a subspace of W. Is it true? Let us see from our question. So if we are to show that, then in our question we are going to realize that V is not a subspace of W. Why? Why is it not a subspace? Remember, there are 3 things we consider for it to be a subspace. We must get a zero vector in V. We must see that addition is closed in V, and scalar multiplication is also closed in V. So let us begin with that vector V with x1, x2, x3, and 1. Those are points which we are looking at in V. But we can also consider, let us say we have V1 and V2, because we need to show something here. If V1 is having those four components, and there are 4 of them because we're talking about 4-dimension space, but we are seeing that V1 and V2, they are members of V. We need to show that is V closed under vector addition. So what do? We shall get V1 and add it to V2. What do we get when we add the 2? You are going to realize we are having x1 plus y1, then x2 plus y2, x3 plus y3, then 1 plus 1. And when you look at that set, it is found in V. Therefore, V is closed under addition, because V1 plus V2 is in V, and it is also in W. So it is fulfilling the first condition, but we must look at the second condition also. What is the second condition? Is V closed under scalar multiplication? So we must check that. If we let C be a scalar, and we have our V already, x1, x2, x3, and 1. So we do a scalar multiplication here, and this is what we are going to have if we do scalar multiplication. So C times x1, C times x2, C times x3, then a C. We need to ask ourselves, do we have this in V? Yes, because we are going to realize that it is still in a 4-dimension space. Therefore, CV is also in V. So V is also closed under scalar multiplication, and therefore CV is also a member of W. Then lastly, we also need to show whether it is containing a zero vector. Is it containing a zero vector? How do we do that? I'm going to force x1, x2, and x3 to be equal to 0. So when I force it to be equal to 0, and I substitute in that set of V, what do I have? I'll have the set of V having elements 0, 0, 0, and then a 1. This is not a zero vector because of the existence of 1 in that set. So whether I force x1, x2, x3 to be equal to 0, I don't get a zero vector. So we don't have a zero vector in V. So what is the implication? The implication is that V is not a subspace of W because it does not satisfy all the 3 conditions. Now we also need to look at part B of our question. And part B of our question, we have V, which is R2, 2. This is for matrix, still almost like R4. And W is the set of all matrices. A equals to A, B, negative BC for some scalar A, B, C, such that matrices are called Skew-symmetric, since AT is equal to a negative A. Now we need to understand something about symmetric matrix, more especially in linear algebra. A symmetric matrix is a square matrix that is equal to its transpose. Such a matrix is called symmetric. And we always see that equal matrices have equal dimensions, and it is only a square matrix that can be symmetric. And when we talk about a transpose of a matrix, this is just a matrix which is formed by turning all the rows of the given matrix into columns and vice versa in order to come up with a transpose. But here we are saying a symmetric matrix is a square matrix that is equal to its transpose. So we need to show that such a matrix V is what? Is a subspace. Is it a subspace? Yes, V is a subspace. Why is it a subspace? We are going to ask the same three questions: whether it is closed under addition. Is V closed under addition? Let us find out. If I consider V2 to be a screw symmetric matrix, and V2 to also be of A2, B2, negative B2, C2, but we're going to realize V1 and V2, they are members of V. If I try to do vector addition, and this is what I'm going to get. If I do vector addition, I'm realizing I'm having A1 plus A2, then B1 plus B2, negative B1 plus negative B2, C1 plus C2. And you're going to see that our addition V1 plus V2 is found in V. It is a member. Therefore, what is the implication? It implies that V is closed under addition. We go ahead and ask the next question. Is V closed under scalar multiplication? If we consider K to be a scalar, and we have our vector V, which is A1, B1, negative B1, C1, a screw-metric matrix. So if I try to do scalar multiplication, K with a V, this is what I'm going to get. I will get K A1, K B1, negative K B1, K C1, and you're going to realize that still KV is in V, and therefore V is still closed under scalar multiplication, since it is still a screw symmetric matrix. Then lastly, we need to look at, is it containing a Z vector? So remember, for screw symmetric matrix or matrices, there's something which is important. Sometimes we call it the antimetric matrix. Is a square matrix whose transpose equals to its negative. That's what we are calling a screw symmetric matrix. And there's something which you must note concerning screw symmetric matrix. Its major diagonal must be 0, since each of its own is its own negative. Therefore, if we are talking about its major diagonal to be equal to 0, that means that A1 and C1 must be equal to 0. But now if I also force B1 to be equal to 0, that means that A1 must be equal to B1, must be equal to C1, must be equal to 0. And that's what I have. And therefore, if I try to substitute in, you realize you have there a 0 vector. So we are having a 0 vector in V, and therefore all the conditions are satisfied. It implies that V is a subspace because it contains a 0 vector, and it is closed under addition and closed under scalar multiplication. Thank you for listening.